session. Let him into this meeting. Okay. Uh, so last time we actually tried to solve some different problems, including eigenvalue equation, normalization of the how we can normalize some function based on the based on their function, and then we try to find that eigenvalue of some function with respect to some operator. Uh, Initially, we started with some basic functions like cos theta or x square dx, e to the power x square, these kind of functions. So today we are going to actually go into deep into some problem solving session, starting from the some summarization of the week 3 lectures, and then we'll discuss some problem. Based on that, we will try to solve many problems. We have set of problems and try to solve those. Okay, so here I'm going to share my screen. Okay, supposed to make it full screen. So- okay, now oh, nice, it's working. Okay. So here we are going to discuss about the hydrogen molecule H2 plus or H2 molecule. Before that, we have to consider that the Born-Oppenheimer approximation, where professor already covered that Born-Oppenheimer approximation. What is that? It means that if a molecule, let's suppose a molecule A2, homoatomic molecule, first of all considering the homoatomic molecule, it having the molecular structure of A nucleus and B is a nucleus, and in between them they have the electron, only one electron. So considering what we considering, the nucleus is rigid. Here the nucleus is rigid, followed by whatever the eigen function we are solving of the electron. Nucleus is rigid. Nucleus is rigid atom. Let me, whoever in lobby, join me. Okay. Someone was there and then he left. Okay. Let me wait for a few minutes if someone is coming. He's here, Surendra. Okay. We already started. I little bit late, so just I'm starting right now. So First of all, we are going to discussing about the Born-Oppenheimer approximation. Okay, you all know that Born-Oppenheimer approximation. In the molecule, oh, why is it clear? In the molecule, nucleus of atoms. So I have to write it further. In the molecules for atom, nucleus nucleuses are rigid and the wave function, Schrodinger wave function, wave function can be calculated as the electron wave function. Electron wave function. This is the Born-Oppenheimer approximation. Whatever we are going to calculate for the wave function, it is the electron wave function, not the nucleus wave function. Okay, so on this time onwards, we are going to calculating only the wave function for the electrons only, not the nucleus. Okay, so this approximation they are considering, and then they are trying to solve the problem for the hydrogen molecule, H2 plus molecule. We have some problem with this with these problems. So let's suppose we have a molecule A, molecule B, and using the Born-Oppenheimer approximation, we are going to solve only the electron wave function for the electrons. So what will be my electron wave function? It is a linear combination of the two atoms. So here linear combination. So my psi of AB will be some coefficient C1 into wave function for the A and sorry, A plus minus C2 electronic wave function for the B. This is the wave function for the AB molecule. Oh, okay. Can we normalize it? Let's suppose it is a hydrogen molecule, a H2 plus molecule. So here you can say all the coefficient will be same, and here's the C1 equals to C2 equals to C. Okay, now we have some problem. Let's introduce the problem. A insert change this one. No. Sorry, I'm not to find. This is one problem. Another problem we have. Let me introduce. Okay. First of all, solve this problem. What is the psi plus? Here the psi plus will be here psi plus is the here the plus combination of this function. So here the psi plus is the psi of plus is to c of bracket open a plus b is a psi. Can we normalize this psi plus and find out the what is the value of the coefficient? It's very easy. We have to normalize it. Let's suppose we have integration 0 to normalization. 0 to infinity. This is psi star. This will be plus psi. It is psi plus, and then we have d tau. It should be 1. As implies, we have 0 to infinity. We have a function psi a plus b whole square means c square into a plus b up. We have 2 sorry a plus b square d tau plus 2 1 implies that we have a is infinity 0 c square a square d tau plus c square b square d tau plus is a 0 to infinity 2 c square a b d tau. Okay, now as the it is a homoatomic, the a dot a square value, it is called as a overlap integral. This overlap integral will be 1. So it is implies that we will have 0 to infinity c square 1. This value will be sorry. This overlap integral will be 1 a square and followed by the c square value. So it will be c square. It will be also c square. And this one is called, this one give you the s, the integral, the overlap integral between the a and b. This is the, let's suppose this is the overlap. This overlap integral is denoted by s. So we have 2 c square into s. Okay, so it's equals to 1. Now what will be my c square? C square equals to 1 upon 2 plus 2s, right? It implies c equals to 1 upon root over of 2 into 1 plus s. Okay, now we have the value of S for the H2 plus molecule molecules, we have S equals to 0.59. Okay, if 0.59, what will be my C value? Now, and without that, what is the C value? C value will be my, supposed to calculate it, 1 upon root over of 2 into 1 plus, sorry, this will be square. No, okay, 1 upon 0.59. Okay, and that will give you the value. Calculate it. Can we calculate? Yes, we can. Let's use the calculator. It will be give you 0.56. Zero point five six. Okay. So in this case, what we can calculate from here, the coefficient for the psi plus, the it will be for a hydrogen molecule, H2 plus molecule, hydrogen cation molecule, they will give you the coefficient value is 0.56. Session. Sorry, I just lost connection and then I log out. Again, I come back and then where I was. Let me share my screen. Okay. I think someone was let lobby. I think nobody is here. Okay. Uh, Sorry, it was my connection issue. And we have, okay, so we have to do the similar thing for the psi minus 1. So what normalization? Let's do the normalization. So we have 0 to infinity psi minus star psi minus d tau equals to 1. That implies 0 to infinity c into a minus b whole square d tau 1. That also implies we have a square integration of 0 infinity a square d tau plus b square d tau minus 2 into infinity ab d tau on 1 equals to 1. Then we have a c square value, and that will give you the, this one is the 1, this one also 1, this one is yes. So it will give me, what is that, 2 minus 2s, right? Okay, so that is true 1, and then we have c equals to 1 upon root over of 1 root over of 1, so 2 into 1 plus s. Oh, sorry, this will be the plus minus. Similarly, previous one also it will be the c equals to plus minus. As it is the positive integer, we are looking for the plus one, so it will be the one function, and then it is giving you uh, only the plus. We have to take the plus one. So for the h plus, what will h plus h2 plus, so the c will be 1 upon root over of 2 into 1 plus 0.59. Sorry, this is the minus. This will be the minus. And what it will give you? Let's calculate. Are you supposed to use my phone? Sorry. Two, two, root. And this two inverse. The value is giving me the 1.1. So from the negative side, size square minus this c value is minus this normalization constant is constant is 1.1, or which H2 plus molecule. Okay, it's okay, fine. So we are able to do it very easily. Okay, then Anybody? The lobby? Okay. Nobody is here. Okay. Okay. Then okay, nobody is here. So let's start the second part. Is the hydrogen atom, hydrogen molecule. For the H2 molecule. So for H2 molecule, what you know, the bonding of the hydrogen molecule, similarly H2 bonding, considering someone is here. Just a minute, let me check. Okay. For H2 molecule, we have a function psi bonding of hydrogen. It is a linear combination of, this is the hydrogen 1, this is the 2. We have a linear combination of, this is nucleus 1, nucleus 2. We have electron here, electron here. We don't know which one is the 1, which one is the 2. Let's suppose one is the 1, another one is a 2. This one is the 1, this one is the 2. So electron is electron 1, U1, that E2, and this one E1. And this is a nucleus 1, nucleus 2. So we have psi of bonding of 1, nucleus 1, and it says psi of bonding of nucleus 2. Okay, so as you know, which implies that my linear combination value is that 1 upon root over of C. What is the C value? We already proved that 2 plus S, 2S, sorry, 2 plus 2S into function for the, let's suppose the wave function is a phi 1 S, phi 1, phi 1 SA is for the 1, and plus phi 1 SP is for the 2. Similarly, we have a, for the side 2, for electron 2, we have a wave function as 1 upon root over 2 into 2S into psi of 1sa 2 plus psi upon 1sb 2. Okay, so then now comes another picture called spin. For the spin, they already introduced is called, what is the, for the spin we have a root over of 2 is spin of uh, alpha, the first one, into beta of 2 minus beta of 1 alpha 2 is the upspin, the alpha upspin, and beta is the downspin. Let's suppose okay, so from it the calculation, the separation special part, the calculation psi bonding will be looks like psi bonding special part will be, don't special, just part will be looks like 1 upon 2 of 1 plus s, and we have phi 1 is a 1, phi 1 is b 2 plus phi 1 is b 1, phi 1 is b 2 plus phi 1 is a 1, phi 1 is a 1 is, sorry, 1 is b 2 plus phi 1 is b 1, phi 1 is a 2. These 4 combination we are getting. So here it is 1 is a 1, 1 is a 2. This is actually giving me, what will give me 1 over, sorry, 2 into 1 plus s, what it will give you, that is 1 of s a 1 to 1 s a 2 plus 1 is b 1, 1 is b 2. We are considering those. 1 is a 1, 1 is b 2 plus 1 is a 1 dot 1, sorry, 1 is a 2. Okay, so these two terms actually overemphasize ionic terms, where the 2 electrons actually at the second electron also is present That means the first term 1s1. The first electron is in atom number 1 A, and the atom number A, and second electron also staying in at the atom number B, atom number A. The second one is that term where the first electron staying at the atom number B, and second electron also staying at the atom number B. That means it is the ionic term. Ionic. It is overemphasized. So our atomic or the molecular orbital, what will be the molecular orbital for the hydrogen molecule? Then we have a 2 hydrogen atom. One, sorry, this is the hydrogen 1 energy state. This is the hydrogen 1. This is the hydrogen 2. It will give me the 2 orbitals. One is the linear combination. One is that plus combination. Another is the minus combination. And 2 will give 2 different combination will give you 2 different energy state. One is called, this is called the sigma, and this is called the sigma star. Okay, and here is the term symbol comes. This is called 1 sigma 1 symmetric, the 2 sigma star. Okay, and if hydrogen atoms, each hydrogen atoms have 1 electron, it will give you the what is that, 2 sigma electrons. And according to Pauli principle, 2 electron in a same orbital will be at opposite spin. This is the Pauli's principle. So my 2 electrons in a 1 sigma orbital will be at opposite spin, and this is actually a singlet state, right? So hydrogen atom is in a singlet state. Okay, now coming to the other molecules for the hydrogen, which I already emphasized. Now what will be the helium plus, now having the molecular orbital MOS of He2 plus. What will be helium 2 plus. Now we have a 1 helium atom, we have a 2 electron in a 1 helium, another electron in another. And here comes a bond order. Bond order. How we can calculate? Bond order actually calculated from the summation of coefficient n of I, summation of I to n, C n I and C I. So what is n? N is that number, n equals to number of, oh sorry, 1 up, number of electron at ith state. C is that coefficient of ith state, ith function. And it will give me 1 upon 2 and two number of electrons is the 2, and it will give me the 1. So here bond order is 1. Now for the helium 2 plus, so we have similarly we have the atomic orbital and followed by the, and it always be, it will give me the another axis is called energy. Similarly over here also, here this is called energy axis. Okay, so how will be electron distribution? We have a helium, we have also helium, and first of all fill the first with a 2 electrons, so we have a 2 electrons. This is called He2 plus, right? So here also similarly, what will be the bond order? Bond order is the will be 2 half of 2 minus 1. So what? 2, right? So here the bond order is half. Now coming to the helium. Oh, sorry, helium 2 molecule. So similarly, draw the molecular orbital. What will be the energy axis? And we have a 2 electron here, 2 electron here. The helium atom, the same of helium 2. Sorry, helium 2. So how it looks like? And we have a 4 electron. Let's build the 4 electron here and here. So we have a bonding energy. Bond order will be my half of, what is that? Half of 1, sorry, 2 minus 2. That will give you 0. So here bond order is 0. And interestingly, if you compare all the uh, four atoms with respect to its with respect to the bond distance, this is the R and this is the energy. The bonding energy for these 4 atoms is looks like we have this helium here, this is helium, so this helium. Now let me change the color, and the helium plus is this is the helium plus, as the bond order is half. Now coming to the He2 plus. So He2 plus, they are also bond order half. So now we take another color. This is the He2 plus, similar to H2 plus. This is H2 plus, and we have last one is the violet one. We have a binding, strong bonding. This is called H2 molecule. Okay, so Why it is so? This is He2 and this is He2 plus. Okay, so why it is so? And here we are finding some bonding in this region. This region is, and the R value, the maximum this R value, this R is around 6000 ppm. So as we know, the has helium atom does not make a molecule with the two helium atom. So why this bonding energy we are getting from the helium atoms? This is because of this internuclear distance of 6000 ppm is coming from the interatomic attraction. This is coming due to the interatomic interaction, right? Okay, so we are able to develop the molecular orbital of the hydrogen, hydrogen H2 plus atom, H2 plus molecule, H2 molecule, He2 plus molecule, and He molecule. Where we found the He2 molecule is not possible because of the energy bonding energy is very high, very less, and bond length is huge. It is around 6000 picometer. Sorry, not it's not the ppm. It is a picometer. Sorry about that. Okay. Now coming to homonuclear diatomic molecules, another where the second 2s orbital is with involved. Let's suppose the nitrogen molecule. Okay, we have a MO diagram of into molecules. How it will be? Back to red. So we have a nitrogen, two nitrogen molecule here. Third, we are actually considering the 1s. This is actually 2s and 2p. P 2s. We are considering the 1s is the inner shell orbital. It's not participating in the forming the molecular orbital. So the outer shell orbital actually participating for the molecular orbital formation. So what will be the molecular orbital looks like? It will be looks like we have a sigma interaction here, sigma interaction, and we have a oh it will three line, and here sigma interaction with px orbital and pi interaction with other two p orbital. Sorry about my drawing. we have sigma here, sigma star. This is the uh this is the sigma, sigma star. We have the pi sigma is pi star, and we have a sigma star. And this sigma star is actually coming from the 2p z orbital. This sigma actually 2p z orbital. This is 2px, 2py, and also pi also 2px, 2py, and this is the 2s orbital, and this is sigma star is the 2s for the 2s orbital. And we have a nitrogen molecule. Nitrogen, what is the electron distribution? Electron distribution is the 2 electrons here, 2s2, right? And 1 electron in each pxpy is pz, sorry. And total number of electrons, here is the 3, here is the 2, 5 electrons, 5, 5, 10 electrons. So let's distribute the 10 electron. First of all, fill the lower energy level, 2 to 4. Here is the 2 electrons here, 2 electrons here, 2 electrons here, right? So here all the 10 electrons at the bonding electron. Now, can you calculate the bond order? Yes, we can go calculate the bond order. What will be the bond order then? Let me check once. You can calculate it. Okay. So bond order will be by half into 2 plus 2 plus 4 plus 2. What will be the value? It will be 3. Right? Okay. So here the bond order is 3. Now we have a problem. Let's introduce some problem. What will be the problem? Let's check once. No, no, no. Okay. Can I solve this problem? Use the molecular orbital theory. I explain the dissociation energy of the nitrogen is greater than the N2 plus. But dissociation energy of the oxygen O2 plus is greater than the O2. Okay, can we do that? Can we explain it? It is super easy. Just consider the bond order and the MO diagram. So what is the bond order? The bonding energy, which is the bonding between the two atoms were actually making the molecules. The capacity of that molecules, bonding capacity is known as the bond order. This bond order defined by some value. Based on that values, we can say the stability of the molecules. Okay. Now our question is, what is the bond order of the nitrogen molecule? As we initially previously discussed, this is the bond order of the bond order of let me full screen bond order uh, in two molecules is 3, right? Now let's solve the N2 plus, right? We have a 2 nitrogen homonuclear, similar energy level, right? 2x, 2p, 2z, 2p, 2z, and the 2s here, sigma, sigma star, 2s, 2s, 2p, 2p. Now we have energy level as follows, and a sigma, sigma star, pi, sigma, pi star, and we have a sigma star. We have 2 electrons here, and here the 2 electrons, and we have a 3 electrons, right? So now fill the electrons. We have a N plus, here we have a nitrogen, and this is the N2 plus. So fill the electron. Total number of electrons is the 9. Oh, sorry, this will be 2 electrons only. And we have 2 to 4. Here is the 6. 6 and 8. We have a 9. Now calculate the bond order. So what will the bond order? We have half of 1 half of 2 plus, sorry, 2 minus 2, 2 minus 2 plus 4 plus 1, right? So here is the will be half of 5, that will 2.5. So the bond order of nitrogen molecule is the 3, and bond order of nitrogen N2 plus is 2.5. So breaking the nitrogen 2 plus bond, 2.5 number of bond breaking energy is much more lesser than the 3. So that means my N2 molecules is much more stable than the N2 plus molecule. So bond order of N2 greater than bond order of N2 plus. that gives the implies that stability of N2 greater than stability of N2 plus, right? Similarly, for the oxygen, and you do it for the oxygen, O2 and O2 plus, we have a 2ps, 2s, 2s, and we have a 2p here. And the bonding. So sigma bond first, and we have the pi bond here. Pi bond, sigma star. This sigma, sigma star, sigma pi, pi star, sigma star. 2p, 2p. Oxygen molecule, we have a 2 oxygen, oxygen. Now we have a 2 electrons here. 1, 2, 3, and 4. So total number of electron is 6, 6, 12. So let's fill the 12 electrons. This number of electrons gone is around 10 electrons. So other 2 electron is in pi orbital, pi star orbital, right? So this pi star orbital actually filled by 2 electrons. So what is the bond order then? So bond order will be my is the half of 2 minus 2 plus 2 plus 4 minus 2, right? And that will give you 2. Now coming for the O2 minus, O2 plus, O plus, and here is the O. Okay, O will be the same. Here 1 electron will be the missing. Okay, so here this electron will be the missing electron. Then it will give you what is the bond order. This is the bond order of O2. Sorry. Bond order of O2. Now change the color. So bond order of O2 plus 3 of 2 plus 2 minus 2 plus 2 plus 4 minus 1. It will give you 2.5, right? So that means bond stability is given by O2 lesser than O2 plus, right? After my question, the bond decision energy O2 is greater than Cn. O2 plus is here we prove the bond stability there, which have the oxygen O2 plus having the bond uh, bond stabilization energy is higher, right? Okay, so from it you can easily solve those problem. Now coming another problem, let's introduce the problem first. The fluorine atom problems. Let me search which one is that one only will be solved. Take the same 4, 5. I lost the problem. Ah, yes. Can I do that easily? Yes. Can. How? Let's just predict the prompt. How we can do that? It is the bond order of the nitrogen. We already discussed bond order of nitrogen. 3, bond order of N2 plus is 2.5 is the bond order of N2 minus. Can you do that? Calculate the bond order of N2 minus. Yes, we can. What will be the value? One unpaired electron in the pi star orbital. So what is the value? So this one will be so 2.5. Right. Now the stability will be N2 greater than N2 minus into this. Right. This is the equation. This is the stability order. We have to just explain it by calculating the bond order of the each molecule. Okay, this is the problem. Another, let's introduce the another problem. Finding problem is a major issue for me right now. Third, so this hard. Ah, can I do this? This fluorine atom. Can I show that the bond dissociation energy for the F2 plus is higher for the higher than the fluorine molecule, F2 molecule. Similarly, just calculate the bond order and it will give you the bond order of fluorine will be higher. For F2 plus will be the higher. So bond order of fluorine is 1 and the bond order of F2, sorry, F2 plus this is 1.5. So bond dissociation energy will be F2 plus greater than 2. This is the F2 flow. Okay, so fine. I think it's very super easy for everyone. Let's move the another topic. Says little bit quantum mechanical. Uh, some introduction with the ethylene molecule, followed by solving some equations, solving some matricular mathematical uh, formation, right? Okay, so now our goal to discuss a little bit about ethylene molecular orbital theory of the MOT for ethylene molecules. Okay, so followed by we'll try to solve by the butadiene and the cyclobutadiene. And now, actually, this is we are considering about the uh, pi orbitals interaction. Okay, so here we call it sigma pi, psi of phi equals to two. We have the two carbon atom here. The carbon one, carbon two, carbon one, carbon two. We have the two hydrogen here. Hydrogen, hydrogen, and with the hydrogen, hydrogen. We are only considering this is with the chi one, chi one, with the function of chi two. Okay, so we are considering this is the C1 chi one plus C2 chi two. The pi orbital interaction. Now, uh, you know, H psi equals to E psi, right? This is pi, this is pi. Can add it. We have a chi one H1 plus C1 C2 2 chi 1 H and 2 2. We give you E C1 bra chi 1 8 chi 2 chi 1 sorry bra chi 1 k chi 1 plus E here C2 into bra chi1 8 chi2. Okay, so this is called H11. Sorry, H11. This is called H12. This is called S11. It's called S12. Sorry, S12, and S12 is known as overlap integral, right? So we can write C1 H1 minus E of S11. We are just taking out one side as a consideration, plus C2 into H12 minus E of 12. Sorry, ES12 is to 0. Okay, here if we left multiple by I1 and integrate overall space. Overall space. And similarly for the chi2, integrate, multiply by chi2 and integrate overall space. So what will give you? It will give us some value C1 H12 minus E of S12 plus C2 into H22 minus E of S2. We are considering that S12 equals to S21, H12 equals to H21 as Hermitian operator. Hermitian operator. As this is the H Hamiltonian operator is the Hermitian operator. Okay, so from it we can make a matrix. This is called matrix. We have a matrix called H11 minus E of S11, H12 minus E of S12, H12 minus E of S into H22 minus E of S22, right? And have coefficient C1 and C2 give me 0. Okay, if non-zero coefficient, so when this matrix in consists of inverse matrix, matrix. So this can be this determinant of this matrix should be 0, right? So and then will give us some the determinant of this is called so the determinant will be 0. Then we have a implies that h11 e s11 h12 e s21 sorry h12 minus e12 and h22 e s22. Oh, sorry, this is matrix, this is determinant, and this determinant is 0. Now you can say h11 as to h12, as it is all the carbon molecules, it is called alpha, and h12 h21 which is called beta, and s12 s21 as to s, and s11 s12 till 1. Okay, so from it we can say alpha minus c, beta minus es by beta minus es, alpha minus c equals to 0. And then this determinant give me e equals to alpha plus minus beta by 1 plus minus s, right? And normalizing the function, as you know, c plus can be written as 1 by root over of 2 into 1 plus s, and c minus will be root over of 1 by 2 into 1 minus s, right? It is already proved the initial days of today's session. Say in that case you can say chi of psi plus equals to 1 by root over of 2 into 1 plus s root chi 1 plus chi 2, and psi minus will be 1 by root over of 2 into s plus 1 into chi of 2 minus chi of 1, sorry, 1 minus chi of 2. Okay, and here the energy E of plus will be alpha plus beta divided by 1 plus s, and E of minus will be alpha minus beta divided by 1 minus s, right? So this is the formulation of the uh, beta ethylene, now coming from the butadiene part. Okay, so we have a fourth term here. Here we can say for the butadiene, what will be, looks like we have ethylene, two ethylene molecule. Okay, So this one is the called chi1, chi2, chi3, chi4. Now we have pi orbital will be called C1 chi1 plus C2 chi2 plus C3 chi3 C4 chi4. Okay, so someone is in lobby. Let me check. Hello. Ah, Virendra. Okay, where I was. Okay, with the butadiene, we know. Now we have to solve the determinant. So what will be the H then? H for the Hamiltonian will be looks like H of 1 1, H 1 2, H 1 3, H 1 4. We have a H 2 1, H 2 2, H 3 2 3, H 3 4. Oh, this is 2 4. This will be the 4 cross 4 matrix. H 3 1, H 3 2, H 3 3, H 3 4. And then H 4 1, H 4 2, H 4 3, H 4 4. So from here we know the H11 is called alpha, H12 the nearby atoms, the our integral will be the integral overall space with respect to the Hamiltonian operator. It will give you the beta. So this H11 is called alpha, H12 is called beta, and then coming the Huckel's rules. Huckel's rules is saying nearby atom, the far away atoms is giving you the overall integral will be 0. The overlap integral will be 0. Then it will give you the 0, and 1 4 also give you the 0. Similarly, 2 1, that means we have a beta, and 2 2 is the alpha. Then 2 3 will be the what will be? It will be the beta. Then it will give you 0. Similarly, 3 1 will be 0, 3 2 will be the beta, 3 3 will be the alpha, 3 4 will be the beta. Also here 0 and 4 2. 4 2 will be the 0. Similarly, 4 3 will be the beta, and the 4 4 will be my 4 4 will be the alpha. Okay, now coming to the identity matrix. Let's introduce the identity matrix. So here we can say H equals to some identity matrix I, alpha into I plus beta into one matrix which is called 0. Value will be 0 1 0 0 and 0. Sorry, this will be the beta. We have the beta here. Here is the beta, so this will be 1. But the beta will be there, that will be the 1, and we have for the alpha it will be given by 0, as the identity matrix they have the only diagonal value is the 1. So this will be this is the 0, Then we have beta is 1 and 0, and 0, 1, 0, 1. Here will be 0, 0. Beta is the 1 and here is the 0. Okay. So now we have to diagonalize this matrix. If you diagonalize this matrix, it will give you the value of is actually computation, or you can do it by your own. It is a undergrad level mathematics, so it is just we have to do the diagonalization of this matrix, and it will give you some value of with a uh, coefficient of is uh, some value c coefficient value that is actually given by something, and I will let you fill it later. And this part will be, this beta part will be, is actually plus 1.62000, and this will be 0 plus 0.6200, and this will be 0, 0 minus 0.62 and 0, 0, 0, 0 minus 1.62, and this coefficient will be some value is known as 0.372, 0.602, 0.602, and minus 0.372. Similarly, second row will be 0.602 plus 0.372. This will be minus 0.372, and should be minus 0.672, 602, sorry. Third row will be 0.602 minus 0.372 minus 0.372 minus 0.602. Similarly, here also 0.372 02 minus 0.602. Oh, sorry, it is plus 602, 0.372. This is called C coefficient, and this one is called diagonalized matrix. Okay, this is diagonalized matrix, and this C actually give you the value of your each wave function for you written as, where is the psi of that, psi1 is actually coming from this coefficient of this coefficient into your the wave function of this chi1, chi2, and chi3, chi4, and depending on this your c value, you can you can derive the four wave function for the butadiene pi orbitals. So this is the phi psi1 that will give you the coefficient. The first coefficient is the 0.372, 0.372 of your Sorry, chi1. Chi1 plus, what is the coefficient next? 0.602. So this will be 0.602 chi2 plus, next coefficient is again 0.602. So with 0.602 chi2 minus plus 0.372 chi4. Sorry, this is chi3. This is psi1. I told you the psi2. Similarly, for the second row, second column, this is 602 plus 372 minus 372 minus 304. 602. So it will be second one will be my second one will be 0.602 chi1 plus 0.372 chi2 minus 0.372 chi3 minus 0.602 chi4 will be the third one. Similarly, we have a coefficient matrix here. The coefficient matrix 602 minus and then plus. So this will be 0.602 chi1 minus 0.372 chi2 minus 0.372 chi3 plus 0.602 chi4. And we have another function. Y function, this is 1. We have a coefficient of minus 0.372 minus 0.602 minus and last one is the plus. So here will be the coefficient 0.30 or 372 chi1 minus 0.6 is that, yeah, 602 chi2 minus 0.602 chi3 plus 0.372 chi4. Okay, so this is the wave function we are getting. Oh, we did some mistake, I think. Let me check some wave function. Yeah, absolutely fine. So based on this equation, we can say the contribution of the each wave function in particular, or in particular a particular wave function orbitals we can uh, easily derive. So what will be the then if you draw the psi1, it will be looks like we have a 4 orbital here. The first one is the contribution will be smaller one, second one contribution will be larger one, third one also larger one, we have smaller one. Now everything is the positive, so everything in the same phase. Let's suppose this is the minus, this is plus, and everything will be minus, plus, minus, plus, minus, and plus. What will be the psi2 then? Psi2, first one is the coefficient is the 602, second one coefficient is the 372, fourth one also 6372, we have it, third one is the 3602. Then we have some change in what is that? Oh, this one will be the oh 3 function. but energy level will be the different. So this one will be the 1, this one will be 3, and this one will be 2. I did some mistake. This one will be 2, and we have 602. We have 51602, and negative. Here is the negative, plus here is the positive, negative, here is the similar, positive, negative, and we have again reverse. So that means here negative and positive. So here we can see that is that we have change in sign here, change in sign here. So we have 1. No. I'm getting confused. I'm sorry about that. This side 2, as it is, whatever it is there. This is side 2, this is side 3. Configuration higher, smaller, smaller, and higher. Plus here the same sign, plus as the sign changed. Here we have one node. It's called node. Similarly, the side 3, the next page. Side 3 will be looks like these two are large, these two are small. Right? From the equation, the coefficient is the first one is the 0.62, and last one is the 0.602. The coefficient will be the large. And then we have the sign change. Here the plus. First of all, this is the plus. Then it will be second term will be the minus. Then we have a minus. Here positive, minus, plus, and here will be again the change in sign here. It will be plus and minus. So here we have two node. Similarly, side 4 will give you side 4 is the first one is the smaller one, second one is the larger one, third one is the larger one. So this will be a small, large, large, small. So here is the negative, positive. Now here is the same sign change. This will give you positive and negative. Here is the again change the sign, plus, minus, and then plus, and then minus. We have a 3 node. 3 node. This one is the plus, right? Yes. This one will be. Okay. So now coming to the butadiene, cyclobutadiene. It is the butadiene. Now coming to the cyclobutadiene. Okay. So for cyclobutadiene, we have a similarly operator H11. This operator. Let's make this operator again once again. Then we will have some alpha beta value will be different. Let's make this operator again. The operator H will be looks like H11. And how it looks like the butadiene. We have a cyclobutadiene 2. Let's suppose chi 1, 1. This is the 1, 2, 3, 4. 1, 2, 1, 2, and 3, and 4. 1, 1, it is the 2, 1, 2, 3, 3, H, 3, 4, H, 4, 1, 3, 4, 4. Okay, this is the matrix we are getting. Now we know H11 to H12, sorry, H22, H33, and H3, H44. Just to alpha. Now put it alpha. This one will be the beta. 1, 3 will be 0, 0. Now 2, 1. No, 1, 4 will be my beta, as 1 and 4 connected. So here will be matrix 2 changes here. This will be the beta. 1, 4, because of 1, 4 is connected here. So this will be the beta. And then 1, 2, this is also beta. 2, 2, alpha. Then again 2, 3 is the beta. And 2, 4 will be 0. Far away. This is the 2, here is the 4. So this will be the 0. Again, now we have 1, 3. 1, 3 will be the 0, as it is far away. Then 3, 2. 3, 2 will be the beta, give you. Then 3, 3 is the alpha. Again 3, 4 is the beta. Now 1, 4. 1, 4 is beta. 4, 1. So this is 4, 1. 4, 1 is the beta. 4, 2 will be 0. 4, 3 is the beta. And 4, 4 is the alpha. This is the matrix we are getting. Again, now coming to the identity matrix, take out the identity matrix and the alpha. So it will give you what it will give you. That can be written as identity matrix alpha into identity matrix I. What is the I? What is I? I is the diagonal matrix which is having only the 1, 0, 0, 0, 0, 1, 0, 0. It is the 0, 0, 1, 0, and 0, 0, 0, 1. As we know from the class 12 level. So this is the identity matrix, and we have a beta. So what will be the beta then? Can be written as, how it will be written as? Can be written as something called, it's a 0, 1, 0, 1, 1, 0, 1, 0, then 0, 1, 0, 1, 0, 1. Sorry, this will be the 1. This will be value of 1, and this will be 0, 1, 0. Okay, so if we diagonalize this equation, this matrix, we will get the coefficient, all the coefficient will be some matrix, and it will give you some diagonalize, only diagonalize value. Other term will be the 0. Okay, so using this one, we also again calculate the coefficient for the butadiene, cyclobutadiene, and based on that we can derive the wave function. So it is can be done by theoretically that compute to make this matrix diagonalize, and it will give you the C matrix, this C matrix, and then it will give you the wave function, the contribution for the wave function. I don't have that data right now. So I think I'll solve this equation in the next class. So its time is time is over right now. It's 5:58. So it will take 20 or 30 minutes to diagonalize this matrix. Next session I will try to solve this diagonalized matrix first. Then we will discuss the next week sessions. Okay. So from here I will like to conclude today's session. If you have any doubts, please let me know. Okay. So I'm stop presenting here. Thank you for listening. We'll come back in the next session. So those okay.